Welcome, Calculus AB. This is section 2.3, derivatives of trig functions and higher order derivatives. This is continued. The essential question is, what's the relation between position, velocity, and acceleration? Let's begin. So derivatives of trig functions, we did sine and cosine before, and now we're doing the other big four. So tangent, secant, cotangent, and cosecant. And here they are right here. So tangent, secant squared, secant is secant tangent, cotangent's negative cosecant squared, and cosecant is negative cosecant cotangent. So you're like, these are kind of random. Like, how do they figure this out? And we can actually discover these using the quotient rule. But I'm going to hold that off for a class activity, or you can do it at home. Just write tangent as sine over cosine and use the quotient rule. But let's just practice using those for today. So for function, I have y equals x minus tangent of x. As a derivative, I can write the y prime equals derivative of x, which is 1, minus tangent. What's tangent? It is secant squared minus secant squared of x. Notice this 2 can be put inside. This means the same thing as secant of x squared. It's just our notation. Now this other one, we have x secant of x, and we're going to have to use the product rule here, where this is our f and our g. So our f prime in this case would be 1, and our g prime, what's derivative of secant, is secant tangent. Secant x tangent of x. So using that product rule, I will say y prime equals 1 times secant of x plus x times secant tangent of x. So we can leave the answer like that. We don't need to write that 1. It looks a little tacky. So secant of x plus x secant of x tangent of x. That's it. All right. Sometimes we can differentiate both these forms differently. So I got y equals 1 minus cosine of x sine of x equals cosecant of x minus cotangent of x. And these are both different ways of writing this. And I want to show you that we can differentiate these both and they'll still be equivalent. So on the left-hand side, this is basically like breaking up that fraction. I'm going to treat this like a quotient rule, where that's my f and a g. That means my f prime would be positive sine x, and my g prime would be cosine of x. So I'm going to do that work for the left-hand side. I will just try to divide this. And what you're going to get is f prime, so sine x times sine x g, minus regular f, 1 minus cosine of x, guess I shouldn't have done that line, times g prime cosine of x. All right, all over g of x squared, so sine squared of x. All right, let's simplify this out. So I'm going to write this as sine squared of x minus, I'm going to distribute this cosine. So it'll be, and then watch this minus, so it'll be minus 1 times cosine of x, so negative cosine of x, minus negative cosine times negative cosine will be plus cosine squared of x, all over sine squared of x. Now, what cancels out, or what simplifies? And you might remember this rule, sine squared of x plus cosine squared of x equals 1. And if you don't, you really should memorize this. I have that up on the top. That sine of squared of x and cosine squared of x combines to 1. So I can rewrite this as 1 minus cosine of x over sine squared of x. All right? And if I broke this up into two separate fractions, I would get 1 over sine squared of x minus cosine of x over sine squared of x. And rewriting that as secants and tangents, that's the same thing as cosecant squared of x minus cotangent x cosecant of x. All right, so that's what I came out to on the left. Now let's just use the right side and just use our rules. See how much easier. So the derivative of cosecant is negative cosecant x cotangent of x. And the derivative of cotangent of x is negative cosecant of x, so I'll have plus cosecant of x squared. And if you look at that, just using that rule, this is the same thing as this. So yeah, it works out both ways. One way was a lot less steps. higher order derivatives. So before we talked about the relation between velocity and position, and we said v of t is equal to s prime of t. Now we're going to talk at acceleration of this mix. So we can find acceleration by differentiating velocity or differentiating position twice. So if s of t is position, v of t is s prime of t, acceleration is v prime of t or s double prime of t. So we're talking about the double prime notation. We got higher derivatives in the first one. So first derivative, we've talked about this. And our second derivative is basically just taking the derivative again, and we write this with notations as you see. So like usually it's double hash mark, so y double prime. The third derivative would be y triple prime. Or you'll see this notation where we put the cube, so the third derivative of y. So you'll see all these different types of notations, all the way down to the nth derivative. So be comfortable with those notations, because any of these are fair game. So let's use that in the application right here, find the acceleration due to gravity. So the moon has no atmosphere. A falling object in the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated a feather and a hammer fall at the same rate at the moon. The position function for each of these falling objects is given right here. S of t equals negative 0.81 t squared plus 2, where S of t is the height in meters. In time in seconds, as shown in the figure to the right, what is the ratio of Earth's gravitational force to the moon's? If you remember for Earth is negative 9.8 meters a second squared. That is the Earth's. So we have to find, and that's like the acceleration of gravity. So we have to find the acceleration of gravity for the moon. And we're going to use this position function. We know our a of t is going to equal s double prime of t. So we got to figure this out. My first step is to figure out my s prime of t, which will be the derivative of this, which will be negative 0.81 times 2, and that's going to give you negative 1.62 t. And that means s double prime of t is going to be negative 1.62. And that is my acceleration at the moon for gravity. Now to find the ratio of Earth to the force of the moon, so we'll do Earth's gravity is going to be negative 9.8 divided by the moon's gravity, negative 1.62. That's going to be roughly equivalent to 6, right? 6. So that is the ratio, roughly. And that's it.